Page hit means physical main memory has a page that CPU requests, and page fault means physical main memory does not have a page that CPU requests. In this visualized example, the page table shows that the virtual pages 1, 2, 7, 4 are loaded into physical main memory, so requesting those pages will result page hit, and requesting other pages will result page fault. Page fault causes an exception. For example, from the valid bit of page table, we know that the requesting virtual page number 3 causes the page fault, and exception handler selects a victim page in physical DRAM to load virtual page number 3. Assuming virtual page number 4 is selected as a victim, the virtual page number 4 is replaced with the physical page number 3. The page table is updated accordingly. Once page is loaded and page table is updated, memory access request restarts and it becomes page hit. Caching pages in virtual memory system works well because of locality that programs have. At any point in time, the programs tend to access a set of active virtual pages, and it's called a working set. The programs with a better locality tend to have a smaller working sets. If working set size is less than main memory size, we expect good performance after compulsory types of page fault. If working set size is greater than main memory, then performance may not be so good with the more page faults. Worst case, the thrashing can happen where the pages are swapped in and out continuously. Let's talk about virtual memory as a tool for memory management. Each process has its own virtual address space, which views memory as a simple linear array, and we map the pages from multiple processes to a single physical main memory. Well-chosen mappings simplify memory allocation and management. In this visualized example, virtual page number 1 of process 1 is loaded to the physical page number 2, and virtual page number 1 of process 2 is loaded to physical page number 8. Because of the use of fully associative configuration, the virtual page can be mapped to any physical page, and this mapping can change dynamically. This mapping scheme makes sharing so much easier. In this example, process 1 and process 2 use the same read-only library code, so we don't load the same page twice, but instead we simply map them to the same physical page once loaded. In this case, the virtual page number 2 from the process 1 and virtual page number 2 from process 2 are mapped to the physical page number 6. By the way, this is a uniform virtual address space layout on 32-bit Linux plus x86. Each section starts at the same location, and there are many other agreements between hardware and software. Let's talk about virtual memory as a tool for memory protection. The idea is simple. We add a permission bits to page table entries in the page table, and page fault handler checks these bits before remapping. If violated, it sends the segmentation fault message. Now let's talk about address translation from virtual to physical address. The virtual memory address is decomposed to the virtual page number and virtual page offset, depending on the size of a page. And address translation means we replace the virtual page number with physical page number while keeping the virtual page offset intact. We access the page table using virtual page number as an index and get the physical page number. We find the page table by accessing a special register called page table base register. On 32-bit machine with the 4 kilobyte page, the memory address space is 32-bit, and because the page size is 4K, we have a low order 12 bits for page offset, and the rest 20 bits are virtual page number. Address translation means we replace high order 20 bits of a virtual page number with the physical page number that we get from page table. Let's take a look at the address translation in case of page hit. First, the processor sends the virtual address to MMU, and MMU fetches the page table entries from page table in memory and translate the memory address. Then the MMU sends a physical address to the memory hierarchy, and memory hierarchy returns the data or instruction to processor. In case of a page fault, the MMU fetches the page table entry from page table in memory, and valid bit is 0, so MMU triggers page fault exception, and the exception handler identifies the victim page, and if it is dirty, then we have to update the disk, and then we load a new page and update the page table entry in memory. And then because the page is loaded, the exception handler returns to original process, restarting the faulting instruction. Now, we ignore the cache, but as a matter of fact, we have multiple levels of cache between CPU and memory. So we go through the multiple levels of cache when we access the memory hierarchy for address translation and for data access. The problem is speed. The address translation takes time, and accessing the memory hierarchy twice, one for address translation and the other for data or instruction, it takes longer time, and the solution is caching. So we introduce a special cache called TLB. TLB stands for Translation Leukocyte Buffer or Table Leukocyte Buffer, and it's a small hardware cache inside MMU, and it contains several page table. It caches several page table entries from the memory hierarchy. TLB hit eliminates a memory access for address translation. For example, CPU issues the virtual address and MMU access TLB cache first using the virtual VPN and gets a page table entry that we need for address translation. And because this is a TLB hit, we don't access the memory hierarchy for address translation. And we are ready to do address translation and get the physical address, and we access the memory hierarchy using physical address to get data or instruction, which is normal memory access. And the memory hierarchy returns the data or instruction back to CPU. So this is the good case. In case of TLB miss, The TLB miss incurs an additional memory access, of course, for address translation. So CPU issues virtual address and MMU access TLB, but TLB doesn't have the page table entry. So we access the memory hierarchy to get the page table entry, and we update the TLB cache, and we translate the memory address, and finally we access memory hierarchy using the physical address, and memory hierarchy returns data or instruction. Fortunately, the TLB misses are rare because of the locality and because of the larger page size and because of the smaller working sets. Here's a brief summary. So each process has its own private linear virtual address space, which cannot be corrupted by other processes. Virtual memory systems use memory efficiently by caching the virtual memory pages from disk to physical main memory, which works well because of locality. It also simplifies the memory management, programming, and protection by providing a convenient interpositioning point to check the permissions.